Welcome to lecture series on heterocyclic chemistry. In this lecture, we are going to discuss a very important name reactions for the synthesis of indole. It is called as a Fischer-indole synthesis. Before discussing the Fischer-indole synthesis, we have covered total 8 name reactions for the synthesis of indole. In part 1, in the first lecture, we have covered Rizard-indole synthesis, Batcol-Limgruber, Medlang-indole synthesis, Nenezescu-indole synthesis, and Bischler-indole synthesis. So these 5 methods were discussed in lecture number 1. In second lecture, we have discussed about a Bartoli-indole synthesis, Gassman-indole synthesis. Both of them involve a pericyclic reactions pathway. Larock-indole synthesis involves a transition metal chemistry. These 3 methods were discussed in lecture 2. Now, in this particular lecture, we are going to discuss a very important, a popular, and a preferred method for the synthesis of indole. Among all available methods available in the literature, the Fischer-indole synthesis is a very popular method for the synthesis of indole. We have already seen that indole is substructure unit of wide range of natural products as well as drugs molecules, and therefore its synthesis is important. As far as the synthesis is concerned, the Fischer-indole synthesis is a very popular method, and therefore we are going to discuss in detail about the various aspects of Fischer-indole synthesis. We will see the general scheme of Fischer-indole synthesis, substrate scope, acid catalysis, examples, and mechanism of Fischer-indole synthesis. Fischer-indole synthesis require phenyl hydrazine as one of the substrate, and there is little difficulty to procure it to procure a substrate phenyl hydrazine derivative, and therefore some modifications have been proposed in the original Fischer-indole synthesis. These two modifications are Job-Klingman modifications, and second one is a Buchwald modifications. Job-Klingman modifications offers diazonium salt as a substitute for phenylhydrazine, whereas Buchwald modifications employs cross-coupling reactions, a technique of cross-coupling reactions to simplify the synthesis of substrate phenylhydrazine. Then, at the end, we will also discuss the applications of Fischer-indole synthesis for the synthesis of biologically important molecules like ondansetron, serotonin, and endometacins. Now, first of all, let us define what is Fischer-indole synthesis is. The acid-catalyzed cyclizations of aryl hydrazone of an aldehyd or a ketone is called as a Fischer-indole synthesis. Here, in Fischer-indole synthesis, we have to start with the phenylhydrazine and enolizable ketone. Now, if these two are heated, we get a hydrazone derivative of the enolizable ketone, and this hydrazone, under acidic conditions, undergoes cyclizations to form the indole derivative. This reaction was invented by German chemist Hermann Emil Fischer in the year 1883. German this Hermann Emil Fischer has made substantial contribution in organic chemistry, particularly in carbohydrate chemistry as well as purine chemistry, and for that he was awarded the Nobel Prize in the year 1902. Now, in Fischer-indole synthesis, if this ketone is symmetrical, then only one product is formed. But if this ketone is unsymmetrical, then usually a mixture of the product is formed. And the outcome of this reaction depends upon the choice of acid, solvent, as well as temperature. Now, to perform these reactions, wide range of catalysts have been employed. The Bronsted acid as well as Lewis acid, both the varieties have been reported in the literature. Among the Bronsted acid, SCl, PPA, acetic acid, ZnC, and among the Lewis acid, ZnCl2, BF3 etherate, these are documented in the literature for the synthesis of indole. Now, in Fischer-indole synthesis, a carbon-carbon bond is formed here, a carbon-carbon bond is formed here, as well as a carbon-nitrogen bond is formed. These two carbon atoms are offered by enolizable aldehydes or a ketone, and this portion is coming from here phenylhydrazine. Now, let us take some of the examples of Fischer-indole synthesis. In this chart, phenylhydrazine is a common substrate. Phenylhydrazine is treated with the enolizable ketones here. Here is a pyruvic acid. We got the hydrazone of pyruvic acid. When phenylhydrazine is treated with the acetophenone, it forms a phenylhydrazone of acetophenone. Here, the phenylhydrazone of ethyl acetoacetate is formed. And once this hydrazone is formed, it is subjected to acid catalysis. Generally, these two are reflux. Phenylhydrazine and enolizable aldehydes or ketones are reflux in presence of an acid or in absence of a catalyst to form the hydrazone. And once the hydrazone is formed, we have to add an acid catalyst for the Fischer-indole synthesis. In all these cases, we have got here substrate indole derivatives with the help of this Fischer indole synthesis. It is the original work of Fischer where this 2 indole carboxylic acid was prepared by using pyruvic acid as well as a phenyl hydrogen in HCl. Now, with the help of Fischer indole synthesis, it is also possible to form a tricyclic derivatives of the indole, and for that we have to prepare a phenylhydrazone of cyclic ketones. Here, cyclohexanone, cyclopentanone, 1,3-cyclohexanedione, beta tetralone, all of them form here a hydrazone derivative, or here in hydrazine type of the derivative. And this hydrazone derivative or in hydrazone derivative on reactions with an acid leads to form an indole derivative, and all these examples are of Fischer indole synthesis. Now let us discuss the mechanism of this reaction. In this reaction, 2 bonds are formed. One is a carbon-carbon bond and a carbon-nitrogen bond is formed. The carbon-carbon bond is formed by the pericyclic reaction process, and the nitrogen-nitrogen bond cleavage is required here, and it is cleaved through the pericyclic reactions pathway, and therefore the mechanism of this reaction is very important. First of all, the reactions of phenylhydrazine with the acetophenone form hydrazone. Hydrazone undergo tautomerism and it forms here in hydrazine intermediate, and this in hydrazine we can call it as enamine also because it's alpha beta unsaturated amine. And so this in hydrazine or the enamine on protonation gives this intermediate. This intermediate is very crucial in the Fischer indole reaction mechanism. It undergoes a 3,3 sigma tropic rearrangement. It is a pericyclic reaction pathway. It is a concerted pathway, and here two things happens in this step. One is a nitrogen-nitrogen bond cleavage, because out of 2 nitrogens of the phenylhydrazine, we require only 1 nitrogen of the phenylhydrazine, and this bond is cleaved here, as well as the carbon-carbon bond is formed. This is a very important stage of the mechanism. So cleavage of nitrogen-nitrogen bond as well as the formations of carbon-carbon bond occurs through pericyclic reaction pathway, and here we get this intermediate. This intermediate subsequently undergo aromatization, and this intermediate later on undergoes cyclizations to form the indole derivative. This cyclization can be described as a 5-exoteric according to the Baldwin nomenclature. A 5-membered ring is formed, this nucleophile is attacking on the trigonal carbon atom, and this double bond is opening on outside of the ring, and therefore it is called as a 5-exoteric cyclization. Later on, liberation of ammonia occurs and we get here 2-phenyl indole. So in this mechanism, in general, the 3 stages are involved. First stage is the tautomerism between the hydrazone and enhydrazine, and second stage is the 3,3 sigma tropic reaction of protonated enamine or enhydrazine to form a carbon-carbon bond and the nitrogen-nitrogen bond cleavage, and later on the loss of ammonia. This mechanism is supported by some evidences, and one of the evidence is about the isotope labeling experiment. If we start with the isotopically labeled phenylhydrazone of this type, this nitrogen is 15, this nitrogen is 14, then this nitrogen which is connected to the aromatic ring is becoming a part of the indole molecule, and this nitrogen which we have seen in the course of this mechanism liberated in the form of ammonia, indeed it is becoming it is not a labeled carbon atom. So this isotope labeling experiment has proved these mechanisms of the Fischer indole synthesis. Now, after learning this mechanism of the Fischer indole synthesis, let us make some little practice on understanding this process. And it is a very classic example where the ortho positions of this phenylhydrazone are blocked here. Still, there is a success of reaction, and therefore we have decided to discuss this mechanism of the reaction. Here again, hydrazone will undergo tautomerism and we will get a enhydrazine. Enhydrazine will be protonated here. So this nitrogen will be protonated, and this protonated nitrogen later on undergo 3,3 sigma tropic rearrangement, and then after forming 3,3 sigma tropic rearrangement, it undergoes 1,2 anisotropic shift. Here it undergoes some rearrangement and we get a new carbocation. Later on aromatization occur here, and after aromatization simultaneously cyclation, spontaneous cyclation will occur, and then ammonia will be liberated and we will get here indole derivative. This reaction is a very important reaction because the ortho positions of both the ortho positions of this phenylhydrazone are blocked, still there is a success of reaction. Now let us take one more interesting example of Fischer indole synthesis. Not exactly the Fischer indole synthesis. It is specifically called as Grandberg synthesis, but it is proceeding again through some Fischer indole synthesis pathway. So first of all, the reactions of phenylhydrazine with this aldehyde form phenylhydrazone here, and this phenylhydrazone undergo here nucleophilic displacement, and we get this iminium ion. Later on here, this proton will be lost, and we will get a new enhydrazine derivative. So the formations of enhydrazine is very wonderful here. The chlorine is involved in the formations of this enhydrazine, and later on it undergoes routine Fischer-Indole synthesis mechanism. It will undergo 3,3 sigma tropic rearrangement, and then it will attack on C double bond N, and this will undergo aromatizations to form here this amino indole compound. Now, what is important in this mechanism, in this reaction, is that generally out of two nitrogens of phenylhydrazine, one nitrogen is lost in the form of ammonia, and one nitrogen becomes the part of indole. Here, both the nitrogens are becoming the part of the same molecule, and therefore this reaction is very important. It is called as a Grandberg in the Grandberg synthesis. Now let us, after discussing the mechanism, now how much we have progressed in indole chemistry. First of all, we have defined the indole synthesis. We have seen that it forms mixture of products if there are more than one indolizable positions. We have seen various examples. We have seen the substrate scope. Then we have discussed about the mechanism of the reaction, and this is also interesting mechanism. Now let us again do some more detailed study of this Fischer indole synthesis, and here we are starting with the aldehydes here, which contains only one enolizable hydrogen. In previous cases, these ketones whatever we are employed, they were containing the two enolizable hydrogens. Here this aldehyde contains only one enolizable hydrogen. So when this is treated with the phenylhydrazine, it again undergo Fischer-Indole synthesis pathway, but here we do not get a completely indole derivative. We get an indolinone type of the derivative here. It's a spirocyclic compound are formed, and this spirocyclic compound, the C double bond N, can be reduced by sodium borohydride to form this indole derivative here. Similarly, the second example is here also. It's only one indolizable hydrogen is present on this site. It forms this hydrazone, and when this hydrazone is subjected to Fischer-Indole synthesis, we are getting a spiro type of the compound. The spiro type of the compound, spiro-indole type of the compound undergo rearrangement reactions using zinc chloride as a Lewis acid, and we get a 7-membered ring attached to this indole nucleus here. Now, as a representative case, we will discuss the mechanism of one reactions where the spiro-indole derivative is formed. So, as usual, this phenylhydrazone will undergo tautomerism to form enhydrazine derivative. This enhydrazine we have to write in a systematic way because this PS group is involved in the reactions, and therefore we are rewriting this structure in this format. This will now undergo 3,3 sigma tropic rearrangement, and this 3,3 sigma tropic rearrangement will form here two things. One is a carbon-carbon bond will be formed, and the nitrogen-nitrogen bond cleavage will occur, and then it will undergo tautomerism, and this nitrogen will attack on the C double bond N, and we will get here indole derivative, and this NH2 will be lost here in the form of ammonia, and we get this spiro type of the compound. Now this spiro compound contains double bond nitrogen is a Lewis base. So this Lewis base will form an adduct with Lewis acid, that is ZnCl2. This is a Lewis acid base adduct, and this Lewis acid base adducts undergo a rearrangement reactions, and we get here a 7-membered ring. So this reaction is very interesting. It's very important as far as the mechanism of this reaction is concerned. Now let us have one more look on the pericyclic processes, various pericyclic processes involved in the formation of indole. Today we have discussed the Fischer-Indole synthesis where the 3,3 sigma tropic rearrangement are involved, and in this carbon-carbon bond formation occurs here, the nitrogen-nitrogen bond cleavage also occurs. Apart from Fischer-Indole synthesis, we have discussed these two reactions in the previous class. One is a Bartoli-Indole synthesis and is a Gassman-Indole synthesis. In the mechanism of these two reactions, again the pericyclic processes are involved. In a Bartoli indole synthesis, a 3,3 sigma tropic reaction is involved, and in Gassman indole synthesis, the 2,3 sigma tropic rearrangements are involved. It is called as a Somlet-Hausser rearrangement. And through this pericyclic reaction pathway, the carbon-carbon bond forming processes is occurring in this indole chemistry, as well as the heteroatom bond cleavage is occurring here. And if we write these two three together, then it is very interesting to watch the importance of pericyclic processes involved in organic synthesis. Now let us one more. Let us discuss once again the substrate scope for Fischer indole synthesis. If it is an unsymmetrical uh, hydrazone derived from unsymmetrical ketone, then there is two way of enolization. There is two ways of formations of hydrazine intermediate. One can enolize towards this methyl, or another can enolize on this ethyl, and therefore two products are formed. And the formation of these two products sometimes depends upon the choice of an acid, choice of solvent, as well as the temperature of the conditions. Here these two representative examples are shown, where we see that this depend upon the catalyst used. It also depends upon the catalyst as well as solvent. Product distribution depends upon these parameters. If you take acetic acid, only one product is formed, and if you take here if PPA, then 50-50% here is formed, and if methane sulfonic acid and P4O10 combination gives the second product, this product as a major one. Now another substrate scope here is on hydrazine derivative component here. In hydrazine derivative component, one can start with the para substrate hydrazine, ortho substrate hydrazine, as well as the meta substrate hydrazine. If it is a para substrate hydrazine, then only one product is formed. In case of ortho substrate one, we also get only one product. Here we have seen 1 to an anisotropic shift occurs, this methyl group migrates. But in case of meta-substrate phenylhydrazone derivative, we get the two products, because the cyclizing can occur on this side as well as it can occur on para to the methyl group, and accordingly the two products are likely to form. Now in the original Fischer indole synthesis, we have discussed that it requires an acid catalyst, but there are certain reports where the Fischer indole synthesis is successful without any catalyst, and it is called as a catalyst free Fischer indole synthesis, or it is also called as a thermal indolization. Now there are certain substrates like this 2 pyridyl hydrazone derivative, or pyrimidine hydrazone, or quinol hydrazone. These are acid sensitive substrates, and because they will be protonated at the nitrogen, and as a result of that, one cannot employ here acid catalysis. And it is observed that even though we do not employ an acid catalyst, there is a success of reaction. For example, this phenylhydrazone derived from pyridine here, it forms this compound in very good yield, 71% yield. Here also this is a pyrimidine derivative to some extent, pyridine derivative. This is also undergoing Fischer indole cyclization, and we get this product. Here in ethylene glycol, this is a pyridine phenylhydrazine derivative. We got here two products. Obviously, cyclization will occur on this side as well as para to the nitrogen, and accordingly, these two products are formed. So Fischer indole synthesis is sometimes successful in absence of acid catalyst also, and this strategy one can employ when the substrate is prone for acid, when it is sensitive to the acidic conditions. Now let us see here some important modifications in the Fischer indole synthesis. We have seen that phenylhydrazine is a starting material for Fischer indole synthesis, but this phenylhydrazine is carcinogenic in nature, and as far as the substrate phenylhydrazines are concerned, they are very less available commercially, and sometimes it is very difficult to prepare them, and if at all they are commercially available, they are very expensive, and therefore it is restricting the use of Fischer indole synthesis for the synthesis of decorated indole molecule, where some substituents on the benzene ring we require, and therefore certain modifications are required. And these two modifications have been proposed. There are several modifications, but these two modifications are very important here. One is Jap modifications, Jap-Klingman modification, and the second one is a Buchwald modification. In Jap-Klingman modification, instead of phenylhydrazine, we have to start with the diazonium salt. This diazonium salt reacts with the reactive compound, as activated compound beta ketoester, and it undergo diazonium coupling, and this diazonium coupling undergo carbon-carbon bond cleavage and carbon-carbon bond cleavage, and then subsequently it forms this hydrazone derivative. So we got now here hydrazone without utilizing the phenylhydrazine, and here the only the diazonium coupling has been employed in the formations of this one. So this is Jack-Klingman modification is possible only when these activated systems like beta ketoester have been employed. Now, once this hydrazone is available with us, we can do now the routine Fischer indole synthesis. So it's under acidic conditions, it will undergo Fischer indole synthesis, and its subsequent post modifications will give us a important biologically active compounds, heterooxygen molecule. Another example here deliberately kept just for making a practice of Jack-Klingman modification. In Jack-Klingman modification, once again, let us see diazonium salts are employed instead of the phenylhydrazine. This diazonium salt undergo diazonium coupling with the beta ketoester under basic conditions. Here the carbon-carbon bond cleavage occurs and we get the hydrazone. And once this hydrazone is formed, then it participates in a Fischer synthesis under acidic conditions. Here is the mechanism of the reaction, and is again very much similar to what we have seen in the previous slide. This amino compound undergo diazotization, we get a diazonium salt, and this enolate anion couples with this, and we get a diazonium coupling here. Carbon-carbon bond cleavage occurs, we get the hydrazone derivative here, and this hydrazone derivative undergo here Fischer synthesis. It forms here in hydrazine derivative 3,3 sigma tropic process. So remaining pathway is analogous to what we have seen in Fischer synthesis. Now another very important modification is a Buchwald modification. In this was reported very recently in the year 1998 by Buchwald, and paper was published in JACS. So here bromoarines have been employed, and range of bromoarines are available in the commercially, and they are inexpensive chemical to some extent. So if we carry out here carbon nitrogen cross coupling reaction of phenylhydrazone derived from benzophenone, we get this hydrazone of benzophenone. Now this benzophenone derivative, if it is treated with enolizable aldehydes or a ketone in presence of an acid catalyst, then there will be exchange of this. It will undergo hydrolysis. We'll get the exchange of this ketone molecule for this hydrazone, and when this will participate, when it will form a hydrazone derivative, then it will undergo a routine Fischer indole synthesis. So this is demonstrated here for 83% product of this particular indole. Here the carbon nitrogen cross coupling is a 97% in presence of a palladium. We got here phenylhydrazone, and this ketone is then exchanged with this, and we get the here indole derivative. That's called as a Buchwald modification. So in this way we have seen the two modifications. One is a Buchwald modification and another is a Jack-Klingman modification. Now let us see the applications of Fischer indole synthesis for the synthesis of some drugs molecule. Ondansetron is a drug molecule to prevent nausea and vomiting during the cancer therapy. Now this ondansetron molecule, if you look at the structure, it contains the indole moiety, and this indole moiety can be constructed with the help of Fischer indole synthesis. Moreover, here is a beta aminoketone, and when it's a beta aminoketone, we employ a managed reaction. So ondansetron synthesis involves two important the reactions as key step. One is a managed reaction, and second is a Fischer indole synthesis. So let us now perform a Fischer indole synthesis first of all. Fischer indole synthesis of phenylhydrazine with 1,3-cyclohexanedione will get this phenylhydrazone. It exists in tautamidazole with form enhydrazine. It undergoes Fischer indole cyclization in presence of ZnCl2. We get this indole derivative. And later on, N-methylation can be carried out by using a base and methyl iodide, this SN2 displacement on methyl iodide, and the managed reactions will be used here. Beta aminoketone, this amino group is quaternized here to make it a living group, and this is again acting as a nucleophile. It will attack on it and will get a ondansetron molecule. So ondansetron molecule is very easy to prepare with the help of Fischer indole synthesis as well as with the help of managed reaction. Second example is the synthesis of endomethacin drug, which is an anti-inflammatory drug. And again here, this indole molecule is prepared with the help of Fischer synthesis. If we do the retrosynthetic analysis, it has to be prepared from N-benzylation here. And this can be prepared from phenylhydrazine as well as a enolizable aldehydes, enolizable ketone here. So the reactions of para-methoxyphenylhydrazine with this ketoester forms this hydrazone. This undergo Fischer synthesis, and later on under acidic condition, under this will undergo benzylation, and we will get here this indomethacin here. Now the last application of Fischer indole synthesis is to some extent a Jaff-Klingman modification. This is a diazonium salt. It is treated with 5-hydroxytryptamine. Sorry, this is treated with this this keto. This is a carbonyl compound. Then it undergo diazonium coupling under basic condition. Decarboxylation occurs here, and we get a phenylhydrazone derivative. This phenylhydrazone derivative undergo here decarboxylation, and as well as here cyclization, we get a Fischer indole product here. Then its opening occurs here, and it undergo here facile it undergo decarboxylation under the condition, as well as the demethylations to form the serotonin molecule. So in this synthesis, the Jaff-Klingman modification is employed, and the molecule is biologically important, and therefore we have included it as a part of discussion here. So we have completed this Fischer indole synthesis in this way. We have seen the definitions of the Fischer indole synthesis. Then we have discussed the mechanism. We have seen the various examples, substrate scope, then modifications, as well as the applications of Fischer indole synthesis for the synthesis of some biologically active compound. Now it's time to check our progress. Students should undertake the practice of writing the mechanism of Fischer indole synthesis. We have written several examples in previous slides. So students should make a practice of writing the reaction mechanism of all these. Here, just 6 examples are given, and its mechanism are already discussed in the previous slide. Then this is another variety of the problem. Here the target material will be given, and the student is asked to write the substrate using the Fischer indole synthesis as a key step. So one can propose if one is a phenylhydrazine and another is a enolizable ketone here. Accordingly, this problem can be solved. Next one is predict the product of reaction. This is because here when it's a para substrate phenylhydrazone, only one product is formed. When it's a ortho substrate, only one product is formed. But when it's a meta substrate, we get the two products. So corresponding products are likely to form in these reactions. Now the synthesis of ondansetron we have made interesting by giving the students certain clues about the molecular formulas of the intermediates. So students should undertake the synthesis of ondansetron by writing the this reaction sequence. So in this way we have completed the synthesis of indole uh, by using Fischer-indole methodology as well as some other name reactions. In the next lecture, we are going to discuss about the various reactions of the indole, particularly the aromatic electrophilic substitution reactions, reactions due to the NH bond. We'll see certain metallation reactions and some oxidation as well as reduction reactions of the indole. Thank you very much for watching the video. Thank you.